Hello, Borden.
Hello.
Where are others? Let's see. So we have a homework 8. That's due on Monday. And there's no more midterm exams, there's a final exam. That's on May 3rd, the Monday of the final week. And the time is 2:45. Do check on the times if possible. Cross check mine, because I have to look into that page and sometimes you tend to make mistakes. Okay. That's Matt and Curtis. And we'll have Christian also here. Okay. So we were doing relativistic formulation, and I want to do collisions, which also appears as a problem in your homework. So let me discuss collisions in general. So remember, this is we want to do relativistic collisions. We remember collisions that you study in your Newtonian physics. You do momentum conservation, you do kinetic energy conservation, and the goal is to get the velocities after the collision. Right. So here, what we have seen is, let's go back to Newtonian physics. Correct? So Newtonian physics, what you would do is if you're interested in a collision of this kind, so that's two mass m1 coming with velocity v1 initial, let's say v2 initial is at rest, so they come and collide, and one could go, so this could be one after collision going v1 final as a vector, and that could be v2 going in another direction. So that's two. If it's an elastic collision, there are two conservation principle. One is that momentum is conserved, and that tells us that P1, so that's M1 V1 initial plus M2 V2 initial. Notice how momentum is being written as mass times velocity, which is no more true in relativity. There it becomes gamma, right? So that's the difference. So this is M1 V1 final plus M2 V2 final. That's your momentum conservation equation, and your kinetic energy is also conserved during a collision. Right, so you would say this is half m1 v1 initial square plus half m2 v2 initial square is equal to half m1 v1 final square plus half m2 v2 final square. And based on this, you can conclude various things. If you're given the initial velocity and the initial velocity of both the masses, you can actually talk about what is the angle at which the second mass will go. And if you know the angle, then you can get the velocities of the two final pieces. Let's not do specific problem there. What we have in relativity instead is momentum becomes mv gamma. So we want to analyze this problem fresh now. So remember, momentum now is P is equal to mass times velocity times the factor gamma there, and which is nothing but m times v over 1 minus v squared over c squared. So that's your momentum. And energy, instead of saying kinetic energy, because there is a rest mass also associated with it, so typically you don't say kinetic energy, but that's an associated quantity in here. So this is a free energy, you can say. So that's the relativistic energy, except for the rest mass also. This is pretty much energy associated with motion. And we have energy E is equal to mc squared gamma. So that's equal to mc squared right, yeah, that's correct. So divided by 1 minus v squared over c squared. And if there is a collision, again we would say that linear momentum is conserved. That means P1 plus P2 is equal to P1 plus P2 after the collision. And the energy will also be conserved. E1 plus E2 will also be equal to E1 plus E2 after the collision. But there is one more quantity that is conserved for each particle in principle. Remember, energy momentum relation tells us that E square has to be always equal, or it's best written in this form, I guess. So these two are the 4 momentum, which is a convenient quantity for us. That's P alpha is equal to E over C and momentum P. So these energy and momentum that I just now told sit as the components of what is called a 4 momentum vector, with the idea that if I were to square this quantity, P alpha, which is nothing but squaring the quantity, that's equal to the mass, negative mass of this particular particle. So it's m square c square, which is equal to negative, sorry, it's equal to negative e square over c square plus p square, magnitude of p square, which is often written as energy square is equal to m square c raised to 4 plus momentum c square. So there is a constraint between energy and momentum, that the difference in the square of the energy and the square of the momentum, with the dimensions taken care of by the speed of light, has to be equal to the mass square of the particle. So how do we use this? So let's do a simple example. This comes in the category of particle physics, where they collide particles with each other and try to find out what are the new particles that can be generated. So let's, before that actually, so let me quickly, so this is, so this is a quick, maybe a crash course on particle physics, maybe. Just to give you a feel for it. Notice that in chemistry, sometime in 1869, I suppose, it was realized that it was Mendeleev who first time noticed this, that all the elements that we knew at the time could be classified as a periodic table. Like we could arrange them in a periodic table, and all the properties can be deduced from where they sit in the periodic table. In fact, during that time, whatever elements were not available, you could actually predict that there must be such an element. Right? If you do not see it yet, you could predict that. Similarly, in particle physics, in the early part of the 20th century, there were lots of particles being created in the lab. Basically, if you have enough energy, you can actually pop out a particle, right? Just because they have mass. If you energy is equal to mass square m square c square, if you have sufficient energy, they could create particles. And now the particles had to be classified, and eventually they learned what this classification was. And here is the classification. So almost everything that we see around us comes out in three different kind of particles. So first is called quarks. And these quarks come in 6 different kinds. There is an up quark. This is an up quark. It's just called U, okay? But it's pronounced as up quark. And then there is a down quark, right? So there's a strange quark. I mean, the name sounds strange, but it is. The name itself is strange. And the associated quark is called charm. And then there is a top quark, and there is a bottom quark. So these are 6 particles if you want. Let me box them, right? And each of them can have an antiparticle associated with it. And as you go to the right, the mass of these particles increases. And as you go to the down, mass decreases. But it's not necessary. Just for your for a relative scale, typically when you're working in this kind of regime, you talk in terms of MeV, mass of an electron. Mass of an electron is equal to 0.5. So this is a unit of mass. In terms of energy, it is MeV. So electron volt is a unit. So that's how you do this is M is of course 10 raised to 6. E is 10 raised to minus 19. So this is 0.5 into 10 raised to 6 times 1.6 into 10 raised to minus 19 joules. Right, that's the amount of energy you need to create an electron. Okay. That seems like a very small number when you think about it in joules, but when you talk about this is the amount of energy you need to create something that's significantly large. But of course, you can have much more energy than that. Proton's mass is about a giga electron volt because it's 2,000 times larger, right? Remember, mass of a proton, just for reference, is 1837, I think, or 1867 maybe. 2 significant digits. It's 1,800 times mass of an electron. And mass of top is larger, and these all fall in that range. Okay, so that's your 6 particles, and remember that each particle can have an antiparticle also, and I'll talk about that in a minute. Another set of particles is where is electrons, correct? So this is these are called leptons. So there is an electron, and for an electron, you associate a particle neutrino. So this is neutrino, which is associated with electrons, so it's called nu E. Right? So that's a nu, letter nu, and with a subscript E. There is a similar particle like electron, which is called a muon. So this is a muon, and there is another particle called tau. So this is called a muon, and this is called a tau electron. And each one has a neutrino associated with it. Just giving a list here. And these are different class of particles altogether. If you want, you must have heard about weak forces and strong forces. The leptons interact with each other by what is called weak forces. Anytime you see a weak interaction, that involves leptons. And anytime there is a strong interaction, that involves quarks. And electromagnetism, which is the weakest, or I shouldn't say it's not the weakest, which involves our photons and electrons, that involves anything among this that has an electric charge. There is what is called a lepton charge. There is what is called a quark charge, which is called the color charge. All those are details, but I don't want to go in there. There is another set of particles that's called gluons, or which is a boson, which is G here. So let me say there are 4 of them. I'll draw that here. This is a standard way of showing this. There is, of course, photons. That's your photon. That's your photon. It's a gamma. Then there is a Z boson, and there is a W boson. All this can be charged. And all this has one new particle, which hopefully you have heard about recently in the last 10 years. This is called the Higgs. The most recent discovery. Most of these other particles were found in experiments by 1980s. The last one was a top quark, which was found in the Fermilab in Illinois in 1996. And Higgs was recently, I think it was in 2010 or something, that it was declared. Okay, that's good. Notice that I have mentioned to you before that particles have anti-particles associated with it. But then one would say that, okay, antiparticles cannot be created. What if you, like hydrogen atom has an electron and a proton, that forms a stable situation, right? But what if you have an antiparticle and a particle forming a stable situation? Is that possible or not? And yes, that is possible. And that's what is called a meson. Anytime any of this quark, for example, so pick any quark and you associate it with another quark, right? So a line above the quark, I mean an antiparticle associated with that. And that you can form a stable particle associated with it, unless it is the same particle. If it's the same particle, it will annihilate and it will create energy, right? So unless it's the same particle, you can actually have a stable situation where you have a quark and an antiquark. And that's called a meson. There's a bunch of mesons that's possible. Then you have baryons, where protons are an example, and where you have 3 quarks. Then you can have a tetraquark. This is very rare. So these two are the most common things that you produce in a laboratory. And you have tetraquark, which basically is 3 quarks plus an quark, 2 quarks plus 2 antiquarks. Exactly like mesons. And there is what is called a pentaquark, which is tetraquark was recently seen, I think, in the last 20 years or so. And pentaquark, I think, is still debated. It is basically 4 quarks plus an antiquark. Okay, so that's your 5 minutes of a crash course on particle physics. Why I introduced that is that now, like in chemistry, all these particles can go from one to the other. And you have collision processes. And let's think of the following collision process. And I want to talk about a pion. So this is a pi, which is positively charged. So this is called a pion, which is a positively charged meson. So basically, I should say not. It's called a pion, but it's basically a meson. That means there are 2 quarks associated with it. We won't need the details at all. We will be just working with the collision problem where momentum is conserved and kinetic energy is conserved. It's just a backdrop that I gave you for the particle physics. This gives you a muon, which is a lepton. So a meson, which is built out of quarks, suddenly decays, and it gives you a muon, and it also gives you a neutrino associated with that. This is a mu. These are just details. So this is a muon. We call this a muon. And this is a neutrino, muon neutrino. Again, this is just a storyline there. For as far as we are concerned in this exercise, there are 3 particles, one decays into the other, right? This is a decay problem. A particle decays into another particle, right? Let's keep this at rest. And just for your information, this is about 140 MeV. Just for a scale, that's about 140. This is about 105 MeV. Remember, electron is 0.5 MeV, so it's about 1,000 times larger, right? Heavier in that sense. And what is muon? Muon is very interesting. For a long time, all the neutrinos were thought to be massless. Like they didn't think they had a mass that, but then at the end of 20th century, it was realized that it does have a small mass. So for our purposes, within our significant digits, this will be zero mass. So this is 0.11 eV. But for our purposes, this will be 0. We will approximate this to 0 mass. And whenever you have 0 mass, remember, energy and momentum become equal, right? Because of this relation that we have, that energy square plus momentum square, or difference in the energy square and momentum square has to be equal to mass. Okay, so what can we conclude? We immediately write down our momentum relation. We have momentum, 4 momentum now, of pi. So this is alpha now. So this, get used to the notation here. There are these Greek symbols representing the particles, and there is a Greek symbol for the index also for the momentum, right? So that's equal to P mu. So mu is not the index of the momentum, it is for the particle, right? So that's alpha plus P nu alpha. What that means is that there is an energy and momentum associated with it. So energy of pi over c times momentum of pi. That's your 4 vector there, right? That's your energy, that's your momentum, is equal to energy of the muon divided by c times the momentum of muon as a vector, is equal or plus, right? Energy of the new, since it's a 0 mass particle, energy and momentum will have exactly the same magnitude. So I can say this will be the magnitude of nu, and this will be the vector nu. And that's because it's a 0 mass particle. If the mass is 0, energy and momentum are exactly the same. One more thing, we can choose, since this is a massive particle, I'm in the lab frame, so when you're decaying, what you expect, a particle is sitting on the table and suddenly it disappears, so it suddenly disappears into 2 other particles. Even if it was moving, you can always go to the rest frame of that particle. You sit on that particle, so you can choose that to be 0. So you can choose your frame to be the rest frame of the first particle. So that means that is at rest. If it is at rest, its momentum is 0. So if the particle is at rest, momentum is 0. That's the first relation you can say. And the energy is equal to mc square, its mass, right? It's completely due to its mass. So let's choose this to be at rest. So I said this is at rest. So there is a simplification here that this is actually 0. So this is 0. And this is basically a mass of the particle times c. Okay. That's 2 equations basically, because there is an energy. One component says that energy is conserved. The second component says that, second means the spatial component say that momentum is conserved, and there is the squared quantities also are there. So we get 3 relations actually. So let me write that down explicitly. So I have mass of the pion times c is equal to the energy of the particle that is created plus the energy of the neutrino that's created, which is basically related to the momentum of that. So that's the energy relation. In a collision, remember, energy is conserved and momentum is conserved. And the momentum part is it is at the rest frame, so it is 0 is equal to the momentum of muon plus the momentum of the neutrino, which implies that these two have the same momentum, right? This implies that which is not surprising if you have to begin with momentum is 0 and there is an explosion, then and if there are only two pieces to the explosion, both of them has to go in two different or opposite direction because momentum has to be conserved. But it's to analyze this problem, if you're interested in the energy, that is a nice way of doing this. So let's go back to our P pi. So let's write down our equation earlier as P pi minus of P mu is equal to P nu, which was all the four components to this, right? Let's square this quantity and we'll see that there is a significant simplification in the analysis that comes up. So let's square this. When we square this quantity, we get P pi alpha, P pi, the momentum alpha squared, right? Just to make clear that there are indices, I'm actually using parentheses. Hopefully it's not too much clutter. When I square this, I have a square of this, I have a square of this, plus P mu, particle P mu, alpha, P mu alpha. Sorry for the clutter. And then there is a crossed scalar product, that's 2 times P of pi alpha times P of mu alpha. And that's equal to P nu alpha, P nu alpha. Remember, the squared quantity of a core momentum is just the mass. Right? P alpha for any particle is equal to minus m squared c squared. Any particle. So at the moment you see the square of a momentum, that is equal to the mass of the particle. So these quantities are all straightforward. So you can immediately say this is m pi, mass of pion times c squared. This is mass of the muon, c squared. This is a dot product. We'll analyze that. So that's 2 times P pi alpha. There is a 2 different particles momentum coming in. We will analyze that in a minute. And the right hand side is the mass of the neutrino, but that's 0, right? Two sig digits, we have 0. We don't worry about that because it is so tiny that it is okay to say it is 0. Okay, so as far as we know, the dot product between 2 muons, we are pretty close, right? We might be able to get how much energy is released in this process. So let's see what this is. This is again a scalar product. So let me do that separately here. So P pi for components is equal. The pion was at rest to begin with, so it is energy is completely in mass. So this is m pi c squared over c. That's f pi c, and since it is 0 momentum, that's equal to 0. That's why we have written earlier. And P mu alpha is equal to the energy of how much energy is released and how much is the momentum of this muon. So what is the product here? So this is equal to, let me write this here. So P pi alpha, P mu alpha, that's this product here, which is, you simply multiply these two, right? C cancels out, and I have m pi times E mu. I have to multiply these two also, but this 0 and a negative sign. Remember that scalar product gives me a negative sign, right? So I should forget that. And plus 0. If I go out of the board, plus 0. That's all. Almost. Okay. So I substitute this in there, and I get pi squared c squared minus, oh, what was this? Was mu, right? Mu squared c squared minus of 2, and this is minus m pi times E mu. And that's equal to 0. So we learned that the energy, how much energy is released, or how much is the kinetic energy of the final particle, which is the muon, is related to completely given in terms of the masses. Mass m mu divided by 2 times m pi. And that immediately tells you how much energy will be released in the process in the rest frame of the lab, correct? And then you know exactly what energy scale to use. This is how you, in an experiment, you will search for this particle in the once there are energy particles emitted, you have to prepare a detector which can detect that much of energy. So you will go ahead and prepare a detector of this much energy and search for it there. And that is how these experiments work. In the last 20 minutes, let me do one more example of this kind, which is nice because this is called Compton scattering. This was one of the first, you might have heard of wave nature and particle nature of light. Of course, Einstein gave the photoelectric effect in 1905, but Compton scattering also belongs to the experiment where the light behaves like a particle instead of a wave. And Compton was actually in St. Louis. He was in WashU in St. Louis, and this experiment was actually done there in 1920s. And he was a very good experimentalist, and he talked about scattering of X-rays of crystals. And if you're interested in scattering, it's a good person to read about. Okay, so let's talk about Compton scattering in very similar manner. Another example of a scattering problem, let's say. And here what we are talking about is there is an electron. So that's an electron. And if whenever there is a massive particle, we can sit on the massive particle and we are in the rest frame, right? So let's sit in the frame in which electron is at rest. So this is at rest, right? So this is at rest. And that's an electron. Let's say there is a photon coming in, and let's say that's 4 momentum is k alpha. forward momentum of the electron can be p alpha, and they come and collide, right? I say collide, this is the Newtonian way of looking at it when we talk about two masses, they come and collide, like two cars come and crash into each other. But this is, we are talking about a photon coming and interacting with an electron. Photon we typically think of as light coming and interacting with an electron whenever we think of scattering. How does it work? But this is, think of a very high energy, when the energy is extremely high, then this is a photon in the sense that it can be thought of as taking up a space, but its momentum is not precise enough. So that's the way to imagine a photon. Here, this experiment shows that it is easy to look at it as a particle instead of a wave. After the collision, think of this as going at an angle. So again, if it is a particle, this has a meaning, otherwise it doesn't have. So this is K prime and the four components. And the electron moves with a momentum and energy. Notice whenever I write alpha, that means it has a momentum and energy. And let's say this is changed, right? It's momentum and energy has changed. So let's say this is angle theta. What are the things we can say if we are in the rest frame of the electron before the scattering? So K alpha, photon does not have a mass, so its energy has to be equal to its momentum, and if its momentum is K, so this is h bar K, and this is h bar has to be magnitude of that K. Maybe I should write that more clearly. And this is h bar times K. It's not necessary that I put an h bar there, whatever is the momentum of the photon, that's what sits there. But now we know that the energy of the photon is described in terms of its frequency. So this is K, with K here. This is given in terms of the wavelength or the frequency. So if light is, when any electromagnetic wave is described in terms of its frequency, that's what we say, red light, blue light, X-ray or gamma ray. So that's what it represents. Okay, so that's your photon, and their energy is having the same magnitude as its momentum because it has zero mass. Coming to the electron, that's P alpha, it's at rest. So its energy is completely in terms of the mass, which is mass of the electron, which is mc, and this momentum is zero because it's in the rest frame. So that's the easy part. After the collision, there is a photon, which again has a frequency associated with it, which is lambda, but it is primed, right? So this is h bar K prime, if you want, or lambda prime. We would like to talk about what is the change in the frequency or the wavelength. But its direction also changes, so there is an angle theta at which it moves away. And there is an electron, prime alpha, which is now it can have energy. So this is energy of energy prime, let's say, divided by C, and that is P prime. That seems like a lot of unknowns, but now what we will do is use the same trick as earlier. We will actually put one particle on the right and rest everything to the left. So let's, so energy and momentum is conserved. So we have K alpha plus P alpha is equal to K prime alpha. So this should be is equal to K prime alpha plus P prime alpha. Notice these are four components, energy and momentum. Each of the component is satisfied. But let me write this onto the left and write this as minus K prime alpha is equal to P prime. That has this feature that when I square this, this becomes a simple equation to deal with. Let me write this as K prime minus K and plus P. So what I have here is that when I square this, I get P square, P alpha, plus K prime, or K minus K prime, which is same as K minus K prime alpha times K minus K prime alpha. And that's the, and I square them, and there is a product, right, cross of that cross terms. So there is a P alpha and K minus K prime alpha. That's equal to P prime alpha, P prime. Remember, whenever I get these squared quantities, they just equal the mass. Right? That's the simplicity in here. The square of this, look at what particle this represents. This represents the electron. This is equal to minus m squared c squared. That's the mass of the electron. This is whatever this is the mass of the photons, or I should say there are cross terms here, right? So maybe wait for one more. Yeah. So let me square this also. So I say K alpha plus K prime alpha, and there is a cross term in there, which is minus 2 K alpha, K prime alpha. And we have 2 times P alpha, K minus K prime. And on the right hand side, this is nothing but the mass of the electron again, because after the collision, the mass remains the same. It is still an electron. That's minus m squared c squared. This represents the mass of the photon. That's equal to 0, because photon does not have mass. This also is a photon. After the collision, it still is a photon. Its energy might have changed, but its frequency might have changed, but it's still a photon. That's still equal to 0. M squared c squared cancels out on the left and the right. A lot of terms goes away, right? 4 terms went away in the whole situation. And what we are left out is with K product of this and product of this, and let's write that down. Together 2 cancels out actually. So this is P alpha K minus K prime alpha is equal to K alpha 2 times K alpha K prime alpha. 2 cancels out. Remember that this is a product of a 4-vector product, so I have to do this appropriate product between P alpha and K alpha and P alpha and K prime alpha. So let me do that. P alpha is MC, so this is minus MC, right? But since it is at rest, it is only the magnitude that contributes. So this is H bar vector K magnitude minus H bar vector K prime magnitude. Because the rest of the components do not contribute, right? Because the electron is at rest, that is not there. What about K alpha? Here, both contribute, but then they don't have the mass, so there is a simplicity in their expressions. So that's minus h bar square times k vector k and vector k prime magnitude, and minus, or plus actually, plus h bar square times k dotted with k prime, using the idea of a dot product between two four momentums. But the dot product between the two vectors is just cosine theta. So everything seems to have a k and a k prime, and there is an h bar that goes away. And let me see what can be done. Let's see. Let me multiply by. Let me divide the MC on the right side, multiply by. This is 2 pi over lambda minus 2 pi over lambda prime. MC, I take it to the right hand side. That's 1 h bar remaining, so it's h bar over MC. And there is 2 pi over lambda, 2 pi over lambda prime. And there is 1 minus cosine theta. The dot product between k and k prime is magnitude of k prime times cosine theta. What that leads to is the denominator, if I make the denominator common, lambda prime, this leads to the equation lambda prime minus lambda. That is the change in the wavelength of the photon during this scattering process is equal to h bar times 2 pi. So that's 2 pi times h bar, which is h bar, remember, is h over 2 pi. So 2 pi cancels out 1. Divided by MC times 1 minus cosine theta. Here, this quantity in here is called the Compton wavelength of an electron. So 2 pi, see this, 2 pi h bar over MC, which is basically h over MC, the Planck constant divided by MC, is called the Compton wavelength of electron. And the scattering process is completely described by that. And to add on to this, I would say a small quiz problem. Is Compton scattering, so the question is does Compton scattering describe wave nature of light or particle nature of light? So in a Compton scattering, does the light behave like a wave or like a particle? Right? Again, the hint was that it played an important role in the early parts of the century, 1920s, where everyone was wondering, can light behave like a particle? And I'll stop here. And that's a good bit of review of relativity. And now we'll go back to E&M and use these properties there, so that in that context, how electric and magnetic field looks to different observers. That's how we want to address these things. Okay, I'll stop here, and thank you.
See you later. Dr. Shodesh,
Yeah.
I'm going to send an email right now after class, but I just want to let you know I do plan on enrolling in that course for the fall. I talked to Dr. Mandal, and it should all work out okay.
Oh, perfect. Okay, perfect. Okay, yeah. I forgot. Yeah, I thought but you had said that you will talk to Dr. Mandal, and so
yes.
it did work out then. Yeah, great.
Yes. Yep. I mean, and he understands too. And he said, since it will be for a course, if I needed to take some time away from the project working with him, he doesn't have anything wrong with, or he hasn't seen any problem with that. So it should all work out. I think it'll be all good. So.
Okay, perfect. So that sounds good. And you understand the commitment involved, right? So it is pretty much work on the project. That's it. Okay.
Yes.
Nothing.
Okay, perfect.
Okay, good.
Sounds good. Yeah, I'll send an email to you and Dr.
Yeah,
Talpat.
that would be good. Yeah, copy it to Dr. Talapatra. I think he will like it. Yeah, he thought about this a lot. Yeah.
Okay. All right. Thank you.
Good. Thanks.
Okay.
Yeah.
Have a good weekend. Bye.
You too. Bowden?
Yeah, I just had a quick question.
Yes.
So the quiz you were asking for if light can behave as a wave and particle.
Of course, that is normal, but I'm asking that in the context of Compton scattering,
Okay.
does the light behave like a wave or a particle?
Okay.
In the context of Compton scattering. Okay.
Okay. Yeah, I think I just missed that part.
Good.
All right. I'll see you next week.
Thank you. Bowden, yes, see you
Thank you.
Monday.